Welcome everyone, my name is Maitrish. I'm going to give a brief seminar on the topic singularity functions and complete set of orthogonal functions from signals and system. So let us see what are singularity functions. Singularity functions are special mathematical functions used to represent a signal which have absurd changes or discontinuities, jumps. They are not in usual sense but are generalized functions. They have described for real life applications. So let us see few types of singularity functions. As we can see here, one type is unit impulse function. The unit function is denoted as del of t, and del of t is given as 0 for t not equal to 0, for infinity for t is equal to 0. As we can see, the property depicts all the value of a signal at an instant and uses a model instantaneous event. So let us see another signal, that is unit step function. Unit step function is another singularity signal. We will see it is not of u of t. It is 0 for t less than 0. It is 1 for t greater than equal to 0. The property is it switches on at t is equal to 0, and the system excitation turns the signal on. So let us see the next one, that is ramp function. Ramp function is denoted as r of t and defined as 0 for t less than 0, t for t greater than equal to 0. The property is linearly increasing. It is a linearly increasing function. It uses is the input of the test system responds to a steady increase system or signal of a system. So let us see the next one, that is parabolic function. The parabolic function is simply denoted of p of t and is 0 for t less than 0 and t square by 2 for t greater than equal to 0. It's a quadratic rising after t is equal to 0, as we can see here. So it is obtained by integrating ramp function, which helps us to study the higher order systems. So let us see the respect to graphs of the systems. Let us see first impulse function. As we can see, for t is equal to 0, it's only giving a value an impulse. Then as we can see here, for t less than 0, the all values are 0. For t less than t greater than equal to 0, if we are getting 1. So as we here we can see the ramp function also. Here the ramp function is studying linearly increasing after the 0, whereas the parabolic function is quadratically increasing. Here we can see the parabolic shape like curve. So here are the brief small drafts as from the above graphs with respect to systems. So let us see the next one, that is the hierarchy of singularity functions. The hierarchy of the singularity functions is given pretty simply. For del function, if we integrate del function, we will get unit step function. If we integrate unit step function, we will get ramp function, and if we integrate ramp function, we will get parabolic function, and vice versa. If we differentiate the parabolic function, we will get ramp function. If we differentiate ramp function, we will get unit step function. If we differentiate unit step function, we will get impulse function. This is how the hierarchy system is decided, and we can see some the integral limits for ramp function, that is minus infinity to t, to get the t of tau, where tau is an constant time variant value. So let us see the next, which is orthogonal functions. What are orthogonal functions? So orthogonal functions give the representation of a set of functions, and we have to find whether the set of a function is orthogonal to each other or not. So here are the conditions for orthogonal function, that is in the given interval a set of function from the function is said to be orthogonal. So here assume the q phi of n of t are the set of orthogonal functions. Let us take one function from here, and if that function is not equal to n, then it is 0. It means the function is orthogonal with respect to this one, and if it is not equal to 0, then the function is not orthogonal. Then let us see what is meant by complete set of orthogonal functions. And the more important point is the given two functions should be independent of each other. This is very important. And whereas for complete set of orthogonal function, let us again assume a set of function, and let us consider another arbitrary signal x of t, and the x of t should be represented in such a way that it is orthogonal to every signal present in this one. So the standard form is this, and let us see the few cases in here. Case 1, we will have for continuous time signal x of t is represented like this, where an is the constant and phi of n of t is the set of the function orthogonal functions, and where an is given as in interval a comma b, so it is given as minus infinity integral a to b x of t phi n of t dt by a to b phi n of square dt. And for discrete time signal, the the signal is represented like this, and coefficient an is represented like this. The only difference is it will have summation k, where k is 0 to n minus 1. So here the examples for continuous time signal is Fourier series, whereas for the case of discrete we will get discrete Fourier series. So let us see a small problem to understand the orthogonal functions very clearly. So here we have given a two functions and x of t also. So we have to represent this x of t in the interval by using the given set. So we will get for two functions in phi's. So first check whether these two functions are orthogonal or not. As we know, we have to apply this formula, phi naught of t into phi 1 of t. So if we apply this, we will get integration 0 to 1 to t minus 1 of dt, and t square minus upper limit 1 to 0, and here we simplify 1 is equal to 0, we will get 0. Hence the given two phi's functions are orthogonal to each other. So let us find the coefficients of the respectives. So let us find c naught. C naught is equal to x of t into phi naught 1, phi naught of t, that is equal to 1 by integral phi naught square. Limits are a to b 0 to 1, which is a to b, that is like this, and 0 to 1, and I square is equal to like this, dt. So we will get square t square by 2, and if we substitute the limits we will get 1 by 2 by 1. Perfect, isn't it? So as we can conclude, the c naught value is equal to 1 by 2. So let us find the value of c1. So c1 is equal to x of t. What is the x of t? It is t into limit 0 to 1, and what is phi 2? That is equal to 2t minus 1 dt by t square means 2t minus 1 whole square dt. Okay, this is what we'll get. If we simplify it, we will get integral 0 to 1 2t to integral 0 to 1 2t square minus t dt by integral 0 to 1 4t square minus 4t minus 1 dt. And if with respect to integrate each term, we will get like this something over the integrals 0 to 1 4t cube by 3 minus 2t square plus 1 of t to 1 to 0. So if we solve this, if we apply the limits, we will get 2 by 3 minus 1 by 2 numerator and 4 by 3 minus 2 plus 1 in denominator. And if we solve this in numerator, we will get this, and denominator we will get this. We cancel 2 times, that is equal to 1 by 2. So we will get c0 is equal to 1 and 1 by 2, and c1 is equal to 1 by 2. Both are same. And x of t, we apply the formula for the s thing, and we will get c0 phi naught of t plus c1 phi 1 of t. This will imply 1 by 2 x of t is given as 1 by 2 into 1 plus 1 by 2 into 2t minus 1. So it will finally gives to t. So hence we have gotten the respective function x of t is equal to t. So let us go to the next one, that is a signal is defined as like this. We have to represent this function in unit stepwise. So here, as I already given the solution, so let me explain the detail. So as we can see here, the limits are for 0 for t less than equal to 0, see from t less than equal to 0 the answer is 0. For the signal increases to at t in the interval 0 to 2, in the interval 0 to 2 it increases to amplitude 2. Okay, perfect. Then from after reaching the 2, it amplitude increases to 4. Let's increase to 4 in the interval between 5, so 5 here, so it remain amplitude 4 in between. Then at 5 it decreases to, for t greater than equal to 5 the amplitude decreases to 0, so at 5 it decreases like this. Perfect. And if we represent this thing in x of t, it is given as like this, so it is given as 2u2 plus 2 of ut minus 2 minus 4 ut minus 5. So here are some small draws here, so let's move on to the keynotes. So the keynotes we conclude are the unit step function, if it is given as like this, then as we know this is the standard form. This from 0 it starts, it is given like this, t minus a, then it shifts to a. Okay, the signal shifts its initial position to a and origin shifts to a. So if the impulse function is given like this, the impulse sets to a. Okay, so if the ramp function is like this, the ramp steadily growth starts from a, not from origin. Then like this, by using these kinds of shifts, reversals, we can these are the building blocks to represent almost any piecewise signal. So thank you, I hope you learned something new in this session.